Okay, with that being said, I should also mention that from the beginning of the March, the class would switch to mixed mode. So you can come to campus and take part in the class in person if you want. And okay, with that being said, let me start. Share the screen. Okay, let's first start by reviewing some of the stuff that we saw in the previous sessions. So when we were talking about the reachability objective, the case where player one's objective is to just reach a target set T, we talked about attractors and traps. And the idea of attractor was basically this set A, which is defined like this. And the intuition was that if you start the game at a vertex inside of A, then player one can actually force the game to visit one target set T. But in this session, what we are actually more interested in is the complement of an attractor. And in previous sessions, I informally said that the complement of an attractor is a trap. And what I meant by that was that player two can basically keep the game here and make sure that player one can never reach any of the target sets T. And we also saw algorithms for computing attractors and traps. We saw that basically the attractor of a given set T can be computed in linear time in order n plus m, where n is the number of vertices of our game graph of our arena, and m is the number of edges. Okay, so let's first talk about what exactly a trap is. So I just want to give you a formal definition of what I mean when I say it's a trap. We didn't need this up until this point because we were always talking about a specific set T, and then we had the attractor of that. But now that we continue with the algorithms for Wookie, we actually have to see many different types of traps. So a trap, and right now I'm again talking from the perspective of player one. So a trap for player one is basically just a set of vertices. It's a set S of vertices such that there is no player one edge that goes out from S to outside of S. For example, this set S would be a trap. And the idea is that if you are player one and if you are at a vertex in this set, for example, if you are here, you don't really have any way of going out of the set. So you're trapped inside the set S. And also the second property of a trap is that every player two vertex in S has a successor in S. So basically player two can also just force us to remain inside the trap. And we usually call this a trap of player one in S. Basically player one is trapped in S, he cannot go out, and the other player always has a choice that allows him to keep us in S. And well, if we have another set T, for example, such as this set T here, which has no intersection with S, we also sometimes call S a trap of player one out of T. So whenever I say a trap of player one out of T, what I mean is that there is a set S that is a trap, and S has no intersection with T. So player one is trapped in S, he can't exit it. Player two can force the game to remain in S. And we also know that this set S has no intersection with our target set or the set T. And of course, we can define a trap for player two in a very similar manner, but we are mostly going to work with traps of player one. Okay, so just to remind you what we were doing in the previous session, we talked about the classical approach to solving Wookie. So we talked about the case where the objective of player one is Wookie of T. So player one wants to visit the set T infinitely many times. And the algorithm that we gave for this particular problem was a recursive algorithm. We started by saying, take your set T, compute its attractor, which we call A, And then the complement of this attractor is a trap. So B is a trap for player one. And the idea was, well, if B is a trap, then whenever we start the game in B, player two wins because it's a trap and he can make sure that we never visit D. But also if we compute the attractor of B, the attractor two of B, which is basically the set of states from which player two can force us to visit B, and call that C, then player two also wins in every state in C. And the idea here was that, well, if we start somewhere in C, because it's in attractor two of B, player two can force us to reach B. And when we reach B, B is a trap for player one, so player two can force us to stay in B forever. So this makes sure that we don't visit T infinitely many times. So we saw that player two has a winning strategy everywhere in C. And then the idea was basically to chop this part of the game off, say that here player two wins, and then recursively solve the problem on the rest of the game. And in the last session, we actually showed that this makes sense, that the rest of the game is a valid subgame, and that the strategies can actually be combined to find memoryless strategies for winning for both player one and player two in the original game. Okay, so this was the classical approach to finding bookie winning sets. And then if you remember, I gave you this pseudocode, which is basically the same as the classical approach, except that we are writing it non-recursively. Instead of doing recursion, we are doing a for loop. And basically, AJ is the A set in our Jace iteration, or the Jace recursive call, and so on. And we also analyzed the runtime of this algorithm and realized that the runtime is order n times m. And here again, n is the number of vertices in our game graph, and m is the number of edges. Now, the main problem that we're going to look at today is how to improve this, how to basically reduce this runtime. Well, because this is a directed graph, the number of edges can actually be the square of number of vertices. So order n times m is, in a sense, order n cube in the worst case, right? So what we're going to do in this session is to try to find an algorithm that is order n squared. So improve the worst case running time by a factor of n. Okay. So I hope you remember this algorithm. This is basically just unrolling the recursive algorithm. At every step, we compute the attractor of the target set for player one. And then we compute a trap, which is the complement of that attractor. And then this is the exact same thing as in the previous slide. So in the trap in BJ, I'm sure that player two wins because he can always keep us there. And then CJ is the attractor two of BJ. So it's basically all the states in the game from which player two can force us to move into his trap. And again, we know that even in these states, player two would win. Okay. So let's see how we were doing actually the runtime analysis here. How did we get to order n times m? Because the first step in getting a better algorithm is looking at how we did the analysis and seeing if we can do any better. So the way we were doing this analysis was that we said, okay, we can compute this attractor in linear time. And we know that from our reachability algorithm. Basically, we had an algorithm for reachability that worked in order n plus n. And this is just complementation. And this is, again, linear time. So we know that every iteration of this for loop takes linear time, takes order m time. And also, we said at every iteration, we are basically finding a set of vertices. We are finding a set Cj of vertices in which player two has a winning strategy, right? And as soon as we cannot find any new vertices, we break. So the idea was that this whole for loop runs for at most n iterations, because there are at most n vertices in which player 2 can win and we can find here. And then every iteration runs in order m. So the overall runtime was order n times n. Okay. But now the crucial observation here is that the only thing that we are using for limiting the number of iterations is that at every iteration, we are at least finding one vertex from which player 2 wins, right? But actually, this algorithm is doing much more than that. If you look at how we are computing these vertices, these sets, so originally we are first computing an attractor, and then we are getting the complement of that attractor. And this complement, bj, this is a trap, right? But it's not just any trap, it's actually the largest possible trap. Because again, going back to our reachability algorithm, so anywhere in the attractor, we know that player 1 can reach T. And when we get the complement of the attractor, this is the largest possible trap, right? Because anywhere outside of this trap, player 1 has a way of reaching T. And so in this algorithm for Bookie, when we are computing these traps, we are also computing the largest possible trap. Bj is the largest possible trap. And then, of course, we're computing its attractor again and going on and adding these vertices to the winning set of player 2. But if you look at the way that we were analyzing this, we don't really need to have the largest possible trap here. We can have any trap. So there is no need in this algorithm to first compute the attractor of T and then complement it to get the largest possible trap. Instead of this, I can just here put any trap, right? As long as I can find the trap, bj, then I can compute its attractor basically, and that's the winning set, and I can remove it, right? So the question is, how can we compute traps? How can we find traps? And can we do it faster than just doing the attractor computation? Also note that there is basically no benefit in finding the largest trap, because the only thing that we were using in the analysis of our algorithm was that this trap is non-empty, that there is at least one vertex in every iteration, one new vertex that we know player 1 has a winning strategy from. So instead of doing this whole costly operation with attractors and so on, what happens if we can find the traps faster? This is the basic idea that we are going to focus on today. And actually, let's be a little bit more exact here. So what we are doing is that we are spending order m time to find a trap. So I'm spending order m time per trap. And then I'm saying that I need at most order n different traps in my whole algorithm, so that the runtime becomes order n times m, right? So what I need here is to somehow limit the time that I spend per trap. And if I can do that, if I can change this m to an n, then that would be great. But that's actually not possible. At least I don't know how to do that. What's a bit nicer is if we can also reason about the sizes of the traps that we have. So basically, what's important for us is how many vertices are getting added to the winning set of player 2 in every iteration. And this assumption that at least one vertex gets added, it's just not strong enough. We want to have a bound on how many vertices get added. So in other words, If I have a way of computing traps much faster, then I will be able to find a much faster algorithm for Bookie. And in order to find an algorithm that is order n squared, what I actually need is this. I need to be able to compute a trap of size k in a runtime that is order nk. Right? So let's go back here and see what I'm talking about. So if I can find this trap and basically do this part of the algorithm in order nk, and if the size of the trap is at least k, then I'm basically uh, paying order n time per vertex that I'm adding to the set W2, which was the winning set of player 2. And because I know that I can add at most n different vertices to W2, then I know that my whole running time is order n squared. So really what's important for us is this. We have an arena, we have a graph game G that has n vertices and m edges. And we also have a given set T of target vertices. And we want to find the trap of player 1 outside of T. And the idea is that if the size of this trap is k, we want our algorithm to run in order nk. This might be a little bit weird because, well, the runtime of the algorithm is actually dependent on the size of the output here, because I'm saying if the output trap size is k, I want the algorithm to run in order nk. But that's fine. We will find such an algorithm. And in this session, we're going to mostly talk about this algorithm, which is basically called hierarchical decomposition. Okay. So before going on, I'm going to just give you some intuition about how we're going to proceed. What we're going to do is that we are going to get this graph G, and we are going to ignore some of the edges. So we're going to focus only on a small subset, let's say, of the edges. And we're going to find the trap using only those edges. Okay, so there is a question. Isn't k less than m? Doesn't it get us to where we were? No. Well, k is at most n, right? Because when I'm talking about a trap is a set of vertices. And every time I find a trap, I'm adding all the vertices in that trap to the winning set of player 2. So I know that I'm at most adding n different vertices to the winning set of player 2. So we have k is less than n, and also the sum of all k over all iterations of our algorithms is also less than n. Okay. So this gives us actually order n squared if we can solve this. Now, so let's continue with our basic idea of limiting the edges that we have in our graph. I'm going to define something called a subgraph trap. And the idea of a subgraph trap is that you fix a subset of your edges, you fix a subset E prime of E, and then player 2 wants to make sure that player 1 is basically not only trapped in a specific set S of vertices, but is also trapped in these edges. Okay. So let me give you the formal definition. So let's say that I have limited my graph and I'm only using the edges in E prime. When can I say that player 1 is trapped inside the set S? And well, of course, I want player 1 to also be trapped outside of the target set. So I want T and S to have no intersection at all, right? But when is player 1 trapped in S? Well, first of all, whenever we have a player 1 vertex inside our trap, inside S, we want to be sure that all of the outgoing edges are in E prime. Why? Because, well, if there is an edge that is that goes from a player 1 vertex and that edge is not in E prime, then player 1 can take that vertex, that edge, And basically, this enables player one to escape E prime, right? So I'm trapping player one in a set of edges and a set of vertices. I'm trapping player one in the set S of vertices and the set E prime of edges. So the first requirement is that player one should not be able to leave my set of edges. So for every vertex V that is in the trap set S and also in the vertex set of player one, all of the outgoing edges are in our limited set of edges E prime. The second idea is, well, the idea of a trap. It shouldn't have any intersection with the target set. So T intersect S should be empty. And then the rest are also very similar to how we defined trap before. So if you have a vertex V inside the trap, and if this vertex belongs to player two, then there should be at least one outgoing edge that remains in the trap. And of course, we want this outgoing edge to be from our limited set E prime, not from the original set E, right? And if we have a vertex V that is in S and in our trap set and belongs to player one, we want player one to be trapped inside the set S. So we want all of its outgoing edges to be inside of S. And well, this one combined with this one says that the outgoing edges are the same no matter if you look at E prime or E. Okay. So this is the definition of a subgraph trap. Now, I can finally tell you what hierarchical decomposition is. So the idea of hierarchical decomposition is that you just create a set of graphs, which I call G0, G1, and so on. And these graphs all have the same vertex set as the original graph G. But they have very few edges. So the idea is that I want G0 to have really few edges, G1 to have a little bit more edges, and so on. Okay, so let's be more formal here. First of all, let's say that I order all of the edges in E. And by order, I just mean that I give them numbers. So I call the edges E1, E2, etc. And I order them in a way that I put some edges towards the beginning of the order. So I put these edges first. And these are the edges from a vertex U to a vertex V, such that U is not a target set, but it's a player two set. Not a target vertex, but a player two vertex. So this might seem very arbitrary at the moment. We will come back to this and you will see why this is useful. But for now, all I want you to keep in mind is that we just have an order on the edges. And that any edge that comes out of a player two non-target set is put first, right? So based on this order, I can actually define a bunch of subgraphs, which I call G0 to G log n, and you'll see why log n. And basically, it's defined as follows. If you look at the graph GI, it has the exact same set of vertices as the original graph, but it has a very limited set of edges, which we call EI. And the set of edges in EI are all those edges that satisfy one of these two conditions. So maybe I should also write or here. Okay. So an edge UV is in EI if one of these two conditions holds. So the first condition is that if I have a vertex U and the number of edges that go out of U are at most 2 to the power of I, then I put all of these edges in my subgraph. I put all of these edges in EI. Okay? So in this case, let's say that I'm computing G2. So 2 to the power of 2 is 4. This vertex U has only 3 outgoing edges. So all of these outgoing edges would be in E2. And the other edges that will be in EI are the first 2 to the power of I in edges of every vertex. So if I have a vertex V, there are probably many edges that are coming into V. And I already had an order on my edges, right? So I just take the first 2 to the power of I edges of this, and I also include this in my set EI. Okay, so can you tell me how many edges a graph GI or the set EI can have at most, based on this definition? So can you give me a bound on, let's say if I look at G5. So this contains all the edges that come from a vertex that has an out degree of at most 2 to the power of 5. And it also contains the 2 to the power of 5 first in edges of every vertex. So what is the total number of edges that this graph can have? And note that the set of vertices is the original set of vertices. So we have n vertices. So basically, for every vertex, if the vertex satisfies this case, I get 2 to the power of I edges. And from this case, I also at most get 2 to the power of I edges. And well, I'm counting some edges twice, but that's fine. So my overall number of edges is order of n times 2 to the power of I. Right? So that's the number of edges in GI at most. And also, how many different graphs GI do we have? We have at most log n of them, right? Because as soon as this 2 to the power of I becomes as large as n, then GI becomes the same as the original graph G. Right? And just for the purposes of this talk, let's say that the number of vertices is a power of 2. So let's just say that n is a power of 2 so that we can have easier algorithmic analysis. I just realized that my video is frozen, so let me do this. Okay, that's not. Okay, so is this all clear? Are you clear about how we are creating these subgraphs? Okay, great. So basically what I had was an initial large graph G, and I created a bunch of subgraphs, and each subgraph has a limited number of edges. So what I want to try to do next is to find traps inside these subgraphs. But before I do that, let me actually show you an example just to make sure that we are completely on the same page about how this construction works. So let's say that my graph G, my original game, was this one. And let's say that I'm showing player 1 vertices with a circle and player 2 vertices with a square. So first we had this ordering of the edges. And in the ordering of the edges, we said that the edges that go out of a player 2 non-target vertex come first. So here the player 2 vertices are this one and this one. This is a target vertex, so I don't care about it. I only care about player 2 non-target vertices. So I only care about this one. And all the edges that go out of this get the first numbers. So this is 1, 2, and 3. And then for the rest of the numbering, I don't really care how the numbering is done. So I just give a number to every other edge. The only thing that I care about is that the edges that come out of player 2 non-target vertices are put first. So this is 1, 2, and 3. Okay, and now let's say that I want to create one of these subgraphs, these hierarchical subgraphs that I talked about. So I want to create, for example, G0, right? So G0 by definition consists of all the edges that come out of a vertex U that has an out degree of at most 2 to the power of 0, which is 1, or the very first in edge of every vertex V. And this is exactly how I'm creating this graph here, this graph G0. So, okay, if you look at this vertex, it has an out degree of 1. So according to the first rule, all of its outgoing edges should be put in G0, and I have put edge number 10 here. The same thing happens to these two vertices because they have an out degree of 1, and all of their edges remain. Now, for the other vertices, so for this one, for example, it has a larger out degree, but, well, what is the smallest edge in terms of the number that is coming into this vertex? So the edges that are coming into this vertex are 8 and 6, and the smallest one is 6, so I keep 6, I don't keep 8. And this is basically how I create my graph G0. So in this case, because the original graph was small and sparse, you see that G0 is quite close to the original graph. But you can imagine if the original graph is huge, then G0 would be a very sparse subset of the original graph. Okay. So this is how we create our hierarchical graphs. And then in each one of these hierarchical graphs, we also color our vertices. And the coloring of the vertices follows a very simple rule. The rule is that I want to distinguish between high degree vertices and low degree vertices. And when I say degree, I'm only talking about out degree. So low degree vertices are the vertices that have an out degree of at most 2 to the power of I. And I color these vertices just white. Okay. And high degree vertices are the vertices that have an out degree of more than 2 to the power of I in the original graph. And I color these based on which player they belong to. So again, going back to this example, 2 to the power of 0 is 1. So for us, a low degree vertex is a vertex that has out degree of 1, and a high degree vertex is a vertex that has out degree 2 or higher in the original graph. And then I assign the colors in the hierarchical subgraph. And the colors that I assign here are basically based on low degree or high degree. So all the low degree vertices are white. High degree vertices that belong to player 1 are blue. And when I say high degree, I mean degree in the original graph. So this is a high degree vertex because its degree in the original graph was 2, right? Which is more than 2 to the power of 0. And high degree vertices of player 2 are colored red. So the intuition here is because we want to create a trap, we know that if we have a low degree or a white vertex, then all of its outgoing edges are actually included in this restricted graph EI as well. Okay, so here's the algorithm that I have finally. So the idea of the algorithm is instead of trying to find the trap in the original graph, let's start with the smallest graph that we have. Let's start with G0 and try to find the trap there. If we couldn't find the trap in G0, then let's add some more edges. Let's go to G1 and try to find the trap there. And let's just continue this until we either get to G log n, which is the same as G, and fail in finding any new traps, or we find some trap in some iteration. But the traps that we're going to find are a bit different. So here's the idea. So let's say that I have a set xi, and let's say xi is the set of vertices that are either blue in Gi, and this means that this was a high degree vertex belonging to player 1, or vertices that are red in Gi but have no outgoing edges. So this is a high degree vertex belonging to player 2, but it has no outgoing edge, right? And then I just, instead of finding an attractor of T, I find an attractor of T union with this set Xi. Now, what is the intuition behind this? The intuition is, suppose that I want to suppose that I am player 2 and I want to trap player 1 inside some set S0, right? And I'm doing this in the graph G0, so the set of edges are only E0, okay? So what are the bad cases for me? The bad cases that I want to avoid is that I don't want player 1 to ever reach a target set. I don't want him to reach T. But I also don't want him to reach these xi's. Why? Because, well, if player 1 can reach a vertex that is blue in GI, what does that mean? Well, by definition, a blue vertex is a player 1 vertex, so he has control about the outgoing edge. But this vertex is blue, so it has high degree, so it has some edges that are in G but are not in GI. So basically, if player 1 can get to this vertex, then he can exit the subgraph GI, and I don't want that. I want to basically trap player 1 inside of the subgraph GI and also away from the target set T. So I definitely don't want player 1 to reach a blue vertex. Why don't I want why don't I want the game to reach a red vertex with no outgoing edges? Well, if the game reaches a red vertex, by definition, the red vertex belongs to player 2. But the problem is that if there are no outgoing edges in GI, this means that all of the outgoing edges of this red vertex are lead outside of the subgraph GI. And this again means that player 2 is forced to exit GI, and we couldn't really trap player 1 inside of GI, right? So this is the intuition here why we are defining this set Xi. And basically the algorithm is that we start with I equal to 0 and try for every possible I. We create the set Xi, and then we try to find a subgraph trap S0 of player 1. We try to trap player 1 outside of T union with this set Xi. And if we can do that, we have found a set S. Well, in this case, it's S0 because in the first iteration, we are working with E0. And then we just return this set S as the trap that we found. Otherwise, we just go to a larger graph in our decomposition and try that. And we continue until either we find a trap or we go to the log n iteration, in which case the graph is the original graph. And if we don't find the trap, that means that there is no trap, right? Okay, so based on that, let me ask you a bunch of questions. So how do we find a subgraph trap? So the idea here was that I have this set S0, which is a trap for player 1 outside of this set T union X0. How do I find such a trap? Well, this is the same algorithm as reachability, right? So I just compute the attractor of T union X0 for player 1, and then I take its complement. And we said that the complement of an attractor is a trap. So I can always find these subgraph traps. Okay. And why is this subgraph actually a trap? So I have this subgraph trap, which is inside the graph GI, and it's trapping player 1 away from T and Xi. So why does it trap player 1 from T in the original graph, in the large graph? And the answer again has to do with the definition of Xi. The way that I defined Xi made sure that player 1 is not only trapped inside this set S, but also trapped inside the small graph GI. So he can never exit GI, so it's definitely a trap outside of T as well. And okay, so the next question is, why does this process even find a trap? Well, if you look at this process, it doesn't really seem like the process is doing anything smart at all. Because what are we doing here? We are basically looking at several different graphs. We are looking at the graph G0, G1 to G log n. and doing the trap calculation in each one of them. But, well, G log n is the same as G by definition, right? So I'm just doing all this extra work for nothing. I could just, as in the original algorithm for Bookie, I could just find the trap in the original graph G, right? So if there is a trap in the original graph G, I will find it, but I'm just wasting so much time there. But why am I doing this time wasting? Well, because there is a chance that I actually find a trap in one of the smaller subgraphs. And if I can find the trap in one of the smaller subgraphs, then I would be much happier. Why? Because, well, let's go back to how much time we spent for reachability. In a graph with n vertices and m edges, the time we spent for reachability and for basically computing attractors and traps was order n plus m. But back in the previous slide, we said that our graph GI has n times 2 to the power of I edges at most. So this is also the runtime for doing for computing traps in the graph GI. And this is much better than the runtime for computing graphs in the original graph, which is basically computing traps in the original graph, which is order n plus m, right? So if I get lucky, and if I find traps earlier in earlier iterations, I have spent less time. And this is also the answer of this question that I had here. What is the runtime of each iteration? The runtime of each iteration is basically just order n times 2 to the power of I. Because what we are doing is that instead of finding the largest graph in the biggest possible, instead of finding the largest trap in the biggest possible graph, we are taking this smaller graph GI and finding the largest trap in GI. We are basically finding this trap. We are basically finding this trap by the same algorithm as we had for reachability. Okay. So now we have this fancy new algorithm for finding traps. And we know that each iteration takes order n times 2 to the power of I. But this is not quite enough yet, right? Because let's go back and see what we needed. What we needed was this. We wanted to also have some idea about the size of the trap that we find. We wanted to have this runtime. Basically, we wanted to say that if the output trap has size k, then I want my algorithm to run in order nk, right? But right now, I still don't have anything about the size of the traps that I find. The only thing that I know is that if I find the trap in iteration I, this is the amount of time that I have spent. Okay. So let's actually find a bound on the size of the traps. But before doing that, are there any questions to this point, or is everything clear? Okay, great. So now that we know how to find the traps, let's figure out what the size of these traps are. So here's the idea. What I'm claiming is that if I find the trap, if I get lucky in iteration I, and I find the trap in iteration I, then I claim that this trap has at least 2 to the power of I minus 1 vertices in it. Now, before proving this, why is this significant? Well, because if this is the case, I'm finding a trap of size 2 to the power of I minus 1, and the amount of time that I'm spending is order n times 2 to the power of I. So I'm basically spending order n time per vertex in the trap that I'm finding. And this would be amazing for our Bookie algorithm, because in the Bookie algorithm, we were just doing this trap computation over and over again and saying that player 2 wins in every trap, right? So now I can be sure that my Buki algorithm becomes order n squared. So the only thing that remains to prove in order to say that I can do the Buki algorithm in order n squared is proving that if I find a trap in the ith iteration, the size of the trap is at least 2 to the power of I minus 1. Okay, so now I'm going to give you the proof, and the proof is basically by casework. So let's consider several cases. And the first case that, well, actually, I guess it's only 2 cases. So the first case that I'm going to consider is if there is a, so let's say that I found this on this other side so that you can see the picture here. So let's say that this is my graph gi minus 1, and this is my graph gi. And let's say that this is the first iteration where I could find some trap Si. Okay. So the first case that I want to consider is if there is a vertex in this new trap Si that used to be blue in the previous iteration in the graph gi minus 1. And remember that if it's blue in gi minus 1, it means that this vertex belongs to player 1, and also its out degree in the original graph was more than 2 to the power of I minus 1. Right? So that was the definition of blue. So what happens if I have a blue vertex of gi minus 1 in my trap set Si in gi? Well, as I just said, there are at least 2 to the power of I minus 1 edges going out of this vertex U, right? Because it was blue, so it was a high degree vertex, so there are at least 2 to the power of I minus 1 edges going out. But this was again blue, so it's a player 1 vertex. And this S is a trap for player 1. So if S is a trap for player 1, all of the successors of this player 1 vertex should also be in S, because otherwise player 1 can just take an edge that goes out of S and get out of the trap, and we don't want to allow that, of course. That's not allowed in the definition of a trap. Well, but if this vertex is in the trap and all of its successors are in the trap, and if it has at least 2 to the power of I minus 1 successors, then, well, the size of my trap is at least 2 to the power of I minus 1. Right? So in this case, the problem was solved very easily. If there is a player 1 vertex in the set Si, which is my trap, that used to be blue in the previous iteration, then there is nothing more to prove, and my trap is large enough. Okay, the next case is what happens if I don't have such a vertex? So every player 1 vertex that I have inside of my trap was white in the previous iteration, because, well, player 1 vertices could either be low degree, in which case they would be white, or they could be high degree, in which case they would be blue. Okay. So this is what I claim. I claim that there is a player 2 vertex U inside my trap, and this player 2 vertex U has an edge to another vertex V, and this edge is in GI. But I also claim that this edge was not present in GI minus 1. So I'm claiming that we have such a situation. We basically have a pair of vertices U and V. U is a player 2 vertex. V, I don't know who it belongs to, and that's why I'm showing it with a diamond. But anyway, there is such a scenario that the edge between U and V did not exist in GI minus 1, but it now exists in GI. And I'm claiming that both U and V are actually in my set Si, in my trap Si. Okay, so why should such a vertex exist? Well, let's say that we don't have any such vertex. Well, if I have a player 2 vertex here in Si, I know that it definitely has at least one successor in the trap, right? Because that's the definition of a trap. Every player 2 vertex has at least one successor in the trap. So the case that we want to prove is impossible is that all of these edges between player 2 vertices and their successors used to be there even in gi minus 1. Well, if that was the case, then because all of my player 1 vertices were also white, so all of the out edges of player 1 were also in gi minus 1. So this Si would also be a trap in gi minus 1. So this is not the first time that I'm finding Si, and this is a contradiction. I could already have a trap in gi minus 1. So this contradiction shows that, again, if the first trap that I'm finding is in gi, and if all the player 1 vertices that are inside this trap used to be white in the previous iteration, then I can be sure that I have this situation. I have a vertex belonging to player 2 that has an edge to another vertex, and this edge was not present in the previous graph. Okay. But what does this mean? So let's look at the definition of the graph gi minus 1. And let's look at it from the point of view of the vertex v. So we said that the first 2 to the power of I minus 1 in edges of v should be in gi minus 1, right? This is, again, just the definition of gi minus 1, this part. Okay. So if the edge from u to v was not in gi minus 1, it means that in the ordering of in edges of v, it wasn't one of the first 2 to the power of I minus 1 edges, right? So I had this edge v, and there were at least 2 to the power of I minus 1 previous edges coming in according to the ordering of the edges that we had. But what was the ordering of the edges? So this is where I'm actually using that assumption on the ordering of edges. I ordered my edges in a very specific way. I said that if u is a player 2 vertex that is not a target vertex, I put the edges that go out of u first, right? And coming back here, so u is a player 2 vertex, and it's definitely not a target vertex. Why? Because it's inside my trap set S. But v used to have at least 2 to the power of I edges before the edge that comes from u. So all of these should also come from player 2 non-target vertices. So W1, W2, so on. These are all player 2 non-target vertices. Why? Because otherwise their edges would not come before the edge from u to v. Okay. So this actually solves the problem, right? Because I have this vertex v, and the vertex v is in the trap. So if I have a player 2 vertex that has an edge to v, then that player 2 vertex would also be in the trap, right? Because of the way that I found my trap. My trap is basically the complement of an attractor. So what this says is that all of these vertices are in the trap, and there are at least 2 to the power of I minus 1 of these. So the size of my trap is greater than or equal to 2 to the power of I minus 1. Okay. So overall, what did we prove? We proved that if we find a trap in step I, then the amount of time that it takes us is order 2 to the power of I times n, and the size of the trap is at least 2 to the power of I minus 1. So this means that I'm finding traps of size k in order nk time. And I can just plug this back into my algorithm for Bookie. Instead of finding the best trap, I just find any trap. So let's say that Bj is a trap of size k. And then the runtime becomes order n squared. So why is the runtime of this algorithm order n squared? Because we can do the same analysis again here. So let's say that we have a trap of size k. The iteration that actually finds that trap of size k takes order nk time, and it increases the size of the winning set of player 2 by at least k vertices. So if you do a simple amortized analysis on the runtime of this algorithm, you can see that the overall runtime is order n squared, because we're basically paying n units of time for every vertex that we put into the winning set of player 2. And we can put at most n vertices in the winning set of player 2. Okay. Yeah. So putting all these things together, we now have an order n squared algorithm for Bookie. And this was all I wanted to teach you in this session. Do you have any questions? Did everything make sense? Okay, great. So now that there are no questions, let me just tell you what we're going to do from this point onwards. So the next session is mostly going to be about parity, and I'm going to give you algorithms for figuring out who wins a game in parity. And by that, I mean that, well, there is a priority function P, and the objective of player 1 is parity of P, and objective of player 2 is its complement, which is parity of P plus 1. And then after that, we are going to mostly leave games alone and go to the realm of automata. We are going to define different types of automata on infinite words, and then there you will also see Bookie automata and parity automata, and you will see the relationship between these. And I will also show you how classical problems on the automata can be reduced to games. So if you want to see whether, for example, an automaton is empty, the language of an automaton is empty, meaning that it doesn't accept anything, I'll show you how that can actually be modeled as a game. And then the next part of the course is about a logical view on verification, which is working with linear time temporal logic, LTL. But the really nice part of the course comes at the very end. And that's when you see that basically using a lot of different reductions, everything that we do with games, with logics, and with automata are actually quite equivalent. So you will have 3 different points of view on a verification problem. You have already seen the game point of view, which was that, for example, in a reachability game, we have a bunch of bad, buggy states, and one player wants to reach those states and make our program crash. The other player wants to avoid this. So this is a reachability or safety game. But then we will also see the other equivalent points of view from the point of view of automata and logics. And the thing that is actually important is that you should really master the algorithms that I'm teaching about games, because we will see variants of them over and over again in the other points of view as well. So the algorithms that we have for automata are very similar to the algorithms that we have for games. Okay, and with that being said, so as I said in the previous session, we're going to spend some of this session and also a little bit time after this session for any doubt clearing. So I'm going to stop the recording now, and